Okay, I hope everyone had a fun fall break, went to Miami or whatever you guys do over fall break. Yeah, welcome back to sunny Philadelphia. And since it's been a few weeks, let me I don't know, try to remember what we've done. So we've been thinking about strengthening marginal guarantees, but so far, even though early on in the class, I wrote down this notation where there's like a distribution over feature label pairs, everything we've done so far has been ignoring the features, right? Like when we talked about marginal mean or quantile consistency, it was, really just about the marginal label distribution. You just need to predict the label correctly on average. And even when we tried strengthening this to talk about calibration, our algorithms just ignored the feature vectors, right? Like calibration is about predicting the label correctly on average, conditional on your prediction, but nothing about what we're asking for refers at all to the features, right? So, but so far this has just been wasted notation. But the features are important when you've got them, right? So we've given maybe sort of the most interesting algorithm we've given so far is for online calibration against an adversary. And we sort of posed this as a way to pass a test by someone who's going to check that you're calibrated to try to falsify the claim that you actually know what you're doing in your weather prediction. And if the only thing they're testing for is calibration, that's 20% of the days when you predict there's a 20% chance of rain, it rains, then you'll pass that test. But there are obvious ways in which you will fail if there are other observable features. For example, the tester could condition on it being cloudy, right? If you're calibrated overall, but if I restrict attention to days in which there are dark and threatening rain clouds on the horizon, all of a sudden you're not even maybe marginally consistent, then it's easy to catch you out. Okay, so what I want to do today is to start thinking about ways in which to strengthen these marginal guarantees that actually make use of these other available features out there. Okay, so what I'm going to talk about today is sort of orthogonal to calibration. We're going to call it group conditional guarantees, but it's truly orthogonal in that we're going to work out what we can say about group conditional guarantees today, but we'll be able to combine those down the road with calibration. These are things you could ask for at the same time. Okay. So,
I just understand what you mean by orthogonal. So these group conditional guarantees, are they not just calibration with respect to groups?
I'm going to ask for something weaker than that to start with. It's just going to be mean consistency, conditional on membership in a group. So rather than a marginal guarantee where I marginalize over everything, I'm going to condition on membership in some group. And I'm just going to ask for mean consistency, conditional on that membership, not calibration, although I could ask for calibration, and we will eventually. Okay, so remember, we've got a feature space, X, that we haven't been using so far, right? So really, our domain is features cross labels. And so I want to think about conditioning on membership in some group, which is really just a subset of the feature space. Okay, so I want to think about a set of groups, which I'll call capital G, which I'll write as a subset of 2 to the x. And a group, a particular group that I'll represent as little g, an element of my collection of groups, big G, will just be represented as an indicator function. So I'll think of little g as just some function mapping feature vectors to 0 or 1, which just, think about that as the indicator, are you in the group or not? Right. So if my group is, the set of dark and stormy days, like, plug in X is a dark and stormy day, this thing outputs 1. Plug in X is not a dark and stormy day, it outputs 0. Okay. Now there's no presumption here. So this collection of groups could be arbitrary. There's no presumption here that they are disjoint. So it's not like, you are a member. It's not like there's, 10 kinds of people and you are exactly one kind of them, right? Like if we're making predictions about people, for example, I could imagine, dividing things up by gender and skin color and income and level of education and, place of birth, language spoken at home, whatever. And these are not, like disjoint. Like if I tell you the answer to, if I tell you someone's membership in one of these groups, it doesn't tell you the answer to membership in the others. Okay, that's going to be sort of important in that a lot of what we're going to talk about today would be immediate if the groups were disjoint, like just, do what we've done previously in this class, but separately for each group. The interesting thing is that we're going to be able to accomplish what we're trying to accomplish even when the groups are not disjoint. Okay. So it's going to be useful to have notation for the set of groups that a particular feature or a particular feature vector or a particular person or a particular day or whatever falls into. So let's write G of X to denote the set of groups that G is a member, that X is a member of. So the set of groups such that, little g of X evaluates to 1. Okay, so I could talk about the groups you are a member of, and I have no idea what the cardinality of that set is, but it's like a sensible thing to talk about. Okay. So, okay, so at a high level, the kind of thing I want to ask for today is like, the kinds of simple things we've asked for in the past, like marginal mean consistency, marginal quantile consistency, but now not just marginally overall, but like conditional on group membership. So like somewhat less marginal than before. Okay. Now, we're going to have to start, we'll have to think about how to define that sensibly if we want to be able to get guarantees from finite amounts of data, because, now I'm conditioning on some event, membership in some group. And if the event almost never happens, if I see almost nobody from, one particular group, right, then I'm just not going to be able to learn very much about that group. Right. So before, when we were talking about truly marginal guarantees, how much I could the accuracy to which I could satisfy them from data depended just on how much data I had. But now it's also going to depend on like how much data I have from each of these groups. So an important quantity is going to be the probability mass each of these groups represents in the underlying distribution. So let's give some notation to talk about that. So under some distribution D, over feature label pairs, a group G has probability mass, let's call it mu of G, by which I just mean the probability when I sample a random member, a random feature vector from this distribution that we're in the group. Okay, so different groups have different probability mass. Okay. And so now let's think about maybe how we should define approximate group conditional mean consistency. Okay. So let's say that a model, which is just some function mapping feature vectors to numbers between 0 and 1, satisfies alpha approximate group conditional mean consistency with respect to some collection of groups G, if simultaneously for every group in our collection, what's true is that when I look at, and I'm going to give like the L2 variant of this definition, but just as we've talked about L1 and L infinity variants, you could imagine something similar here. What should be true is that, well, we satisfy marginal mean consistency conditional on being a member of the group. So when I look at the difference between the expectation of our prediction conditional on being a member of the group and the expectation of the label, the true label, conditional on being a member of the group, and I look at that squared, this should be less than, okay, and here is where I'm going to make a choice in how to define things. This should be less than alpha over mu of G. Okay, so I'm allowing larger error on smaller groups. Okay, right, so, like if I just said, alpha is 0, let's ask for like marginal mean consistency. This would just be like the obvious definition. It's just mean consistency on the conditional distribution once we condition on membership in a group. The only place where maybe I'm like making a judgment call here and might be up to some funny business or something is when I'm defining what I mean by approximate group conditional mean consistency, where I'm explicitly allowing larger error on smaller groups. But I claim that this is like the right way to parameterize things. How come? Well, let's maybe like jump ahead for a moment and start thinking about how we might go about even like testing a condition like this on data. Well, what would we do? We would take like a data set. We would estimate the quantities inside of here, right? The average value of the label, the average value of a prediction, conditional on being a member in some group. And those quantities, we could like relate the in-sample quantities on our data set to the distributional quantities using something like a Chernoff bound. And what would we get? We would get that our error was something like 1 over the square root of the number of samples we had to compute these empirical estimates. Well, okay, what's the number of samples we have? Well, it's just like, the total size of our data set times the times the probability mass of the group, right? Because only a fraction of our samples are members of the group that we can use to estimate this quantity. Okay, so the error of our estimates would sort of be something like, would sort of increase at the rate of 1 over the square root of the size of the group. And that's exactly the scaling we're asking for here, right? If you take the square root of both sides, that we're thinking about an absolute quantity here, then I'm asking that I'm allowing that this quantity sort of grow larger at a rate of 1 over the square root of the size of the group, which is sort of the limits of our estimation error. Okay, so not only will this be a, as we'll see in our derivations, be a mathematically convenient definition, like, our change in potential function will sort of work best at this scaling. This is sort of the right notion if we're thinking about estimating quantities from data, because our estimation error of these quantities already scales like the error we're allowing here. Okay, does that make sense? Okay. So maybe let's now remember back to some of our early experiments trying to come up with an algorithm for calibration. And sort of we eventually figured out that if we were really just asking for calibration, applying this sort of kind of iterative algorithm that we're going to talk about again was like the wrong thing. Like, you know, if we just wanted calibration because the buckets, you know, the conditioning events over which calibration is defined, like the different predictions of the classifier, those actually are disjoint events, then it makes sense to sort of just have this like one-shot calibration algorithm that we sort of figured out on the fly was better than the iterative thing. But let's remember how the iterative thing works, because it's going to come in handy again. The iterative algorithm sort of, what did it do? It looked for sort of violations of the condition that we were aiming for, which was at the time calibration, meaning it looked at like a conditioning event, like, you know, a level set of the predictor on which our current predictor conditional on that like event was not marginally mean consistent. And then it applied like a patch operation that just shifted the predictor on that conditioning event to make it marginally mean consistent. And we sort of said, okay, well, you know, there's like a potential argument, like, you know, since each of these shift operations decreases the Breyer score, we make progress and this thing converges. Okay, so we're going to try to do the same kind of thing here. The group, you know, the conditioning events are no longer disjoint, which sort of breaks the sort of immediate attempt at doing all of the updates simultaneously, but the iterative algorithm still makes sense. Okay. So let's define the kind of patch operation that's going to be useful here. We'll call it a group shift patch. Okay, so given a model, F, a shift delta, which is just a number, and a group G, the group patch applied to the model, applied to F with shift delta is just the following function. I'll call it H of X, and it's parameterized by the model we're starting with, the group, and the shift. And it's just the model that outputs f of x plus delta if x is in the group G, if g of x is 1, and outputs f of x otherwise. Okay, so it's doing what it says. Start with this model F. If I want to like shift it on some group by delta, then all of the on all of the examples for which the example is in the group, the output of H is just F shifted by delta, f of x plus delta, and for examples not in the group, the output is unchanged. It's just f of x. Okay, makes sense. Okay, so let's try to do the obvious thing. Let's call this algorithm group shift. It'll take as input an initial model, an approximation parameter, and a collection of groups. And its goal is to find a model that satisfies alpha approximate group conditional mean consistency. And it's going to do exactly like the first thing you would think of. It'll say, does my current model satisfy approximate group conditional mean consistency? If not, find a group on which the condition is violated, shift it to fix the violation, and then continue. Okay. So it's going to be an iterative algorithm. It'll be keeping track of some model FT. At round 0 initially, F0 is just F, whatever you started it with. And T, the iteration, is 0. And we'll keep going while our model fails to satisfy alpha approximate G conditional mean consistency. And well, if it doesn't satisfy group conditional mean consistency, there must be some group on which the condition is maximally violated. So let's find it. Let's let G of T be the group that maximizes over all groups in the collection G that we want to make promises with respect to. The product of the size of G, the probability mass of G, times the difference between the conditional mean and prediction conditional on G. So times the difference between the squared difference between the expectation of Ft of x conditional on being a member of G and the expectation of y conditional on being a member of G. Okay, so like if we were G conditionally mean consistent, like the definition would be that all of these quantities were 0, but we're not. So there has to be, like by definition, one of these quantities that is at least alpha. And so we're going to find the largest one. And in particular, it's going to be at least alpha. Right? That's like the definite, it comes out of how we parameterized our definition, right? For all, if we don't satisfy marginal mean consistency, then if we multiply on both sides by mu of G, it's got to be for some group that this product is greater than alpha. Okay. So we've identified a group on which, like, that's sort of witnessing a large violation of our constraint. Now we can think, like, what's wrong on what's our model doing wrong on this group? So let's say that delta T is just sort of a measure of our mean consistency violation on this group. It's just the difference between the expected value of the label conditional on being in the group minus the expected value of the prediction conditional on being a member of the group. Okay, but, this would be 0 if we were marginally mean consistent, but like we're not, so it's not 0. And then, how are we going to update? Well, we're just going to apply a group shift patch to like fix this problem. Okay, so we'll let tomorrow's model, Ft plus 1, just be equal to the model that we get by applying a group shift patch to today's model, Ft, and this group that we found, and this shift that we just computed. And we'll update the bookkeeping so that we recognize that it is now tomorrow. And we keep doing this until we break out of the loop, if we ever break out of the loop, at which point we output the current model. Okay. Is the algorithm clear? It's sort of like the obvious thing, right? You're just like myopically, you're saying, look, I've got this condition I'd like my model to satisfy. Doesn't satisfy the condition. Let's find the sort of place on which it's like maximally violating the condition. And let's myopically perform the update that causes it not to satisfy, not to violate the condition anymore. Okay. And although many of you can probably at this point guess what the analysis is going to be, let me just point out why a priori, if you hadn't like seen me do this a bunch, it might not be obvious that this thing even halts, right? And it's because these groups are not disjoint, right? These groups are intersecting. And so I'm fixing a problem on one group, but I'm changing, possibly making the problem worse on a different group, right? Like when I apply a group shift patch to GT, now I'm making sure that I satisfy group conditional mean consistency conditional on GT, but like there might be some other group G prime that intersects with GT for which I've now actually made things worse, which could actually happen, right? These are like arbitrary intersecting groups. So like what we need to argue, like obviously if this thing outputs something, then by definition, that's the halting condition. It satisfies group conditional mean consistency. But the kind of thing you should like worry about is that we're like chasing our own tail. We're fixing a problem here, we're making a problem worse over there, we're fixing it over there, we're making it worse over here, and that this goes back and forth forever. Okay, so we need to convince ourselves that that's not happening. Okay. And so like, what does it mean to convince ourselves that that's not happening? We need to observe somehow that we're making monotone progress according to some measure, right? So like, it's actually not clear that we're making monotone progress according to group conditional mean consistency. Like it's not clear that we're becoming more and more mean consistent as we go on in a monotonic way. So that's not going to be our potential function. But we've already studied updates like this. What we're going to argue is that each of these updates makes a significant improvement in the squared error of the model, in the Breyer score. And that's why we can't cycle. That's why it has to converge quickly. Actually, each of these updates makes us better in Breyer score, even if it might make us worse in the measure we're actually trying to satisfy, like group conditional mean consistency. Therefore, there can't be very many updates. And therefore, even if it makes things worse locally, we know for sure they'll have to get better eventually because it'll halt quickly. And the only way it can halt is if it satisfies the condition that we want. Okay. So what's the lemma? So for, all of the quantities defined as in the algorithm, if I look at the change in Breyer score, the change in squared error between round T, so the Breyer score for FT and the Breyer score for FT plus 1, so the sort of change in Breyer score, decrease in Breyer score between round T and T plus 1, this is going to be exactly the product of the size of the group that we've identified at round T times the squared magnitude of the shift. Okay, this is sort of the key to it. This is like our progress lemma. It's going to let us know that we're not chasing our tail. Okay, so we've seen proofs like this before. Let's figure out why this is. And it's, like crucially using the fact that the Breyer score is separable. It's an expectation. Okay, so I can partition space up into any like disjoint partition that I want, and I can like, take the expectation of the squared error on the first part, weight it appropriately, and add that to the expectation of the squared error on the second part, weighted appropriately. How should we break it up? Well, in this case, it makes sense to break it up by whether examples are members of group GT or not, right? So the groups themselves don't partition the space because they're not disjoint, but certainly I can partition the space into two parts based on whether you're in one particular group or not. That's what we do. Okay, so this is just, you know, the sort of change in squared error on these two models. I can write that as the expected change in squared error conditional on not being in group G times the probability that I'm not in group G plus the expected change in squared error conditional on being in group G times the probability that I am in group G. Right, like this is just some way I can write out an expectation of anything over a partition of the distribution. Okay, now first term is easy, right? What's the first term evaluate to? So change in squared error conditional not on being in group G. You're doing some kind of obscenity, but okay, 0, got it. So this is 0, right? Because like by definition of the patch operation, we haven't changed the model there, right? So the, you know, conditional on not being in group G, ft plus 1 equals ft. So this difference is, you know, pointwise 0 everywhere. So it's only the second term that contributes to the difference. Okay, so what is the second term? Well, the probability that we're in group G, that's just mu of G. And we know what ft plus 1 is conditional on being in group G. It's just ft plus delta. So we can write that out. This is just the expected difference of ft of x minus y squared and ft of x plus delta t minus y squared, okay, all conditional on being in group G. Okay, here we've just noted that once we condition on being in group G, ft plus 1 of x, the result of this patch operation is just a linear shift. We shifted all of the points in that group. Okay. Okay, so we can just like work out what this difference is. You know, like there's going to be some terms that cancel, like this y squared that goes away. And so what we get is that, and I guess the ft of x squared also goes away. So what we get is just the cross terms. What we get is 2 delta t times the expectation y minus ft of x conditional on being in group G. Okay, so that's like the cross term from here and the cross term from here. Minus delta t squared. That's just the sort of squared term from here. Okay. But what is the expectation of y minus ft of x, conditional on being in group G? That is the definition of delta, the expectation of y minus ft of x, conditional on being in group G. So this is just equal exactly to mu of G times 2 delta t squared, one from here, one from here, minus delta t squared, which, you know, if I've got 2 of something and I take away 1, what do I have? I have 1. So it's just mu of G times delta t squared as claimed. Okay, so we make monotone progress on Breyer score. In fact, we make like kind of fast progress because you know, mu of G times delta t squared, the amount of progress we make, it's guaranteed to be what if the algorithm hasn't halted yet? Mu of G times delta t squared. So we've shown that we make like some kind of progress if we, you know, turn the crank once. The question is alpha, exactly, right? Because like if I'm not alpha approximately group conditional mean consistent, that means that multiplying through by mu of G, there must be some group for which mu of G times delta t squared, this is just delta here, is bigger than alpha, right? Because alpha approximate group conditional mean consistency is just the condition that it's less than alpha for all of them. And we're updating on a group that maximizes this product. So it's at least, we found a group that's at least alpha. So it's not just that we're making some like little bit of progress, we're actually making alpha progress. Yeah. And so we can end up with the theorem that given any model F, and given any collection of groups, doesn't matter what they are, they can intersect in arbitrary ways. Think of it as rain or shine, you know, humidity, temperature, race, gender, ethnicity, language, income, whatever. And any degree of approximation alpha, yes, you know, should be strictly bigger than 0 that you want. This algorithm over here, group shift, halts after at most 1 over alpha many rounds. And output something ft that satisfies alpha approximate group conditional mean consistency. And the Breyer score of the model that it outputs will be equal exactly to the Breyer score, well, no, sorry, will be smaller than the Breyer score of the model that it started with minus t times alpha. Okay, so I think I won't even, I'll just talk through the proof because it's basically just a couple of observations on top of this lemma. First of all, Breyer score for a model that is, making predictions between 0 and 1 for labels that are between 0 and 1 is just some number that's between 0 and 1. Can't be bigger than 1, can't be negative. If the algorithm hasn't halted yet, then in particular, the current model isn't alpha approximately group conditionally mean consistent. And so in particular, there must be some group G for which this product is at least alpha. That's like just a rearrangement of the definition of not being group conditionally mean consistent. We perform a patch operation on that group. Now, when we perform a patch operation on that group, we decrease the Breyer score by exactly the product of the size of the group times the magnitude of the shift squared, which was the thing that we selected our group to maximize. Now, this could be even bigger than alpha. We don't know what this is. It could be even bigger than alpha, but we know it's at least alpha because it's by definition, this must be at least alpha for some group. Otherwise, we would be group conditionally mean consistent. So each round of this decreases the Breyer score by at least alpha, possibly more. Breyer score starts at 1, can't go below 0. So there can't be more than 1 over alpha many updates. Otherwise, we'd definitely be negative. In fact, right, you could refine this and say it's less than the Breyer score of the initial model over alpha, right? So 1 over alpha is some worst case you would get if your initial model was maximally terrible and you managed to get a perfect model. But in fact, you expect the number of updates to be much better. In particular, even if this is still going to drive error to 0, it can't be more than the initial squared error of your model over alpha because it's starting from there. So you'd expect this, if you're starting with a decent model and your problem's not perfectly predictable, you'd expect this to be a very small number of updates, in fact. And each update improved the model as measured by squared error by at least alpha, maybe more. So if you had t updates, the error went down by t alpha.
You sort of touched on this when you're describing this t, but there's something kind of interesting with two results in that it sort of makes it seem like there's this you either can have if it takes a faster amount of time than you want, then your actual Breyer score is going down by less, right? So these are only one of them is really strong at a time, right? Is there, and this tension doesn't actually exist, right? So if it happens to be the case that I'm able to do it in fewer rounds to get to the conditional mean consistency, then will I tend to have higher Breyer score error?
Good. So that's a good question, maybe leading into our next algorithm. And of course, okay, you can obviously do all of this for quantiles, and maybe I'll show you that at the end, which is sort of what goes the way you'd expect. But let me now skip over that for a moment and show you how to improve upon this algorithm and get the thing, to Natalie's point, that exactly minimizes Breyer score, at least amongst the class of models that this kind of procedure can output, which are basically concatenations of shifts of this sort, right? You could ask the question, right? So maybe to rephrase Natalie's question, we've sort of analyzed this algorithm in a very local way, where we sort of say, okay, every time there's an update, it decreases the Breyer score by some amount that we don't totally understand. We can upper bound the amount it decreases it. It's at least alpha, but different group could be different. And so you could imagine that there's path dependency. Like maybe if I update on one group first, then I get alpha approximate group conditional mean consistency after 2 updates. But like if I'd only picked another group first, it would have taken me 10 updates, and I would have actually preferred that because I would have gotten a lower error thing. So we could sort of ask, okay, can we understand what's going on and try to say, well, there's some well-defined model class that this thing is outputting a model from. We'd have to think about what that is, but it's sort of models that can be arrived at starting from F by applying these patch operations in any order. Can we come up with somehow a direct optimization algorithm, not this local iterative thing, that directly finds the thing in this model class which minimizes Breyer score, and therefore, by a similar kind of argument, must also be group conditionally mean consistent? And the answer is yes. Okay.
I don't know if it's close or not, but here we are doing this algorithm conditional on the fact that we know the true distribution for X and Y.
Yeah.
Is it obvious that this one is going to work when we have empirical distribution?
By the end of the class, I will give you an out of sample theorem. But to locally convince yourself that the answer is yes. The reason it's going to work is basically because of how we defined alpha approximate. The way we defined it was, I don't care about shifts smaller than, 1 over root the size of the group, right? So what do you need to do to run this thing from data? And again, we'll prove theorems like this by the end of the class. But basically, you need to estimate this quantity from data. Now, estimating this quantity from data, okay, so first of all, these things are averages, right? So Chernoff bounds, as we've seen, will tell us that if we have enough samples from the group, then our in-sample estimation of the mean will be close to the true mean. The concern is that the group is very tiny, and so I don't have enough samples from the group. But that problem goes away because the thing that we're estimating is multiplied by the size of the group. So basically, you can estimate each of these quantities to something on the order of, to error on the order of 1 over root the size of the group, which means that when you square it, the error is on the order of the size of the group, and we multiply by the size of the group. Okay, so that's so the answer is yes, you can do this from the empirical distribution. What I'm going to show you now is a different, simpler algorithm, and that's the one I'm going to analyze the out of sample performance for, but you could do it for this one too. Make sense? Okay. So, bloobity blah, blobbity blue. Okay. So addition is commutative, right? I can, A plus B plus C is the same thing as C plus A plus B is the same thing as, there's some other orders too. What are these group patch updates doing? They are only adding, they're only sort of doing additive shifts on a group. Okay, they're not conditioning. These aren't the calibration updates. The shift is not conditional on any property of F. It is conditional only on being a member of the group. Okay, so whether or not you are a member of the group is invariant to whether it's round 3 of this algorithm or round 10 of this algorithm or round 12 of this algorithm. Oh, before we talk about this, let me just say another thing that, otherwise it sort of is worth marveling over. You might have worried a priori that asking for group conditional mean consistency was going to get maybe harder and harder and harder the more groups I asked for. Right, like there's a lot of groups out there. Like, you know, like there's doubly exponentially many groups.
Sorry, that's just going to change the mu, so it's not going to be.
Well, not necessarily. I could have a lot of big groups, right? It's not like the groups don't partition the space, right? I could have, there's a whole lot of groups, each of which are, yeah, exactly. Like there's a zillion groups, each of which contain half the population, right? So there's like a ton of groups, even if I restrict myself to groups that aren't tiny. And so, when I ask for like group conditional mean consistency, I'm applying and like I'm asking for a number of constraints on my classifier that, is like linear in the number of groups, which could be huge, right? And yet the number of iterations, so you might think like, okay, I'm gonna like have to like, even if I don't chase my tail, even if I'm not like getting into cycles, you might think like, oh, well, like I might not satisfy this constraint on any of the groups. I'm gonna have to like touch all of them. I'm gonna have to fix all of the problems. But the number of iterations that this algorithm runs for is entirely independent of the number of groups. It's saying even if you have a zillion groups and you don't satisfy group conditional mean consistency, like on any of them at the outset, like run this thing for 1 over alpha many rounds, and you will satisfy group conditional mean consistency no matter how many groups there are. Okay, so like, I mean, you can sort of, the analysis is very simple and transparent, but like, you can, if you stretch your imagination, imagine a world in which that wouldn't have been true, right? It's sort of amazing that you can satisfy all of these constraints, no matter how many of them there are, in a number of iterations that is entirely independent of that.
So the steps are independent, but if you're actually going to build the algorithm, you need to keep track of the groups and you need to search every time, right?
That's right. So there is the computational step, and this also comes up in the sample complexity in a mild way, of finding the group that has the largest violation. But, at least if we think of having direct access to the distribution for now and don't worry about computation, there's still, I don't know, what I think of as the somewhat magical thing that, it's sort of a little bit of a game of whack-a-mole, right? Like, I'm finding these constraints and I'm whacking them, getting rid of them, and I might cause others to pop up elsewhere. The total number of whacks is like independent of the total number of moles. So I don't know, seems neat. Yeah. Anyways, so that you can all marvel appropriately. Okay, so what was I was talking about addition being commutative. So, right, like as I'm whacking these moles, right, like the same mole could come up several times, right? Like I could at round 5, I could like, deal with like group G star, and then at round 10, I could deal with group G star again, right? Because subsequent updates might have made things worse for this one group, right? So I might several times over the course of this algorithm perform an update on the same group. But because addition is commutative, it doesn't matter the order in which I did these things, right? Like if I sort of think about sort of updates that correspond to that group, they're additive, right? Okay, so let's write, I'm going to be referring to quantities for the algorithm I just erased, but it was like written on this same board, so they live on. Let's say that lambda G is the sum over all of the rounds such that the group that was selected on that round was group G. And what I'm summing up over is the shift value that I applied at each of those rounds. Okay, so some particular group could have shown up at round 1 and round 12 and round 18. And for each of them, I applied some a group shift operation on that group for some shift, these could be positive or negative. Okay. But like, I don't care about the order, addition's commutative. Let me just add up those shift quantities and call that lambda G. Those were the shifts applied to group G by the algorithm. Okay, then I claim that like the final model output has the following form. It is just, and I'm going to write it as now a function that's parameterized by lambda, which think of it as a vector with one entry for every group. It is now just f of x plus the sum over all of the groups of lambda G times G of x. Okay, so what I'm claiming is what's a different way to evaluate the exact same function output by this group shift algorithm? Well, just sum up the shifts applied to each of the groups. In general, remember, like marveling again, we expect this to be like a sparse vector, right? Like the dimension of the vector could be huge. It could be a ton of groups, but there was only 1 over alpha updates in total. So like only 1 over alpha of these entries could possibly be non-zero. Doesn't really matter, but just something to marvel at. Okay, then how can I describe the function output at the end? Well, there was the model I started with. So how do I evaluate the function output on x? Well, there was the model I started with. Let's compute f of x. And then, like, I was a member, this example is a member of some of the groups, and it's not a member of others. It experiences the cumulative effect of the shifts that I've applied for each of the groups it is a member of, and not for the groups that it's not a member of. For the groups that it's not a member of, this term is 0 because g of x equals 0. For the groups that it is a member of, g of x equals 1. And what we're saying is, okay, for this example, it was shifted by each of the shift values that were applied at any round corresponding to rounds for which that group was selected. And it doesn't matter the order in which we apply those shift values, again, because addition is commutative. So it's just lambda G. The shift corresponding to that group is just the cumulative shift the algorithm applied to that group. And so it's just lambda G. Okay, now an example can be a member of multiple groups, right? So it could experience shifts, cumulative shifts corresponding, of course, to all of the groups it is a member of. That's why we need to sum up over all of the groups it's a member of. But alternately, like I can always write the model output by this group shift algorithm in this form. Okay, people buy that?
Could lambda G be different depending on what path the algorithm takes?
Absolutely, yeah. So I'm not claiming anything about like uniqueness or whatever. Right now, I'm just making an observation that to the extent that we want to understand like the hypothesis class of the algorithm, like the kinds of things it might output, like the only thing it can output are things that have this form, okay? Like f of x plus some weighted linear combination of like group indicator functions for the groups that the example is a member of. Okay, makes sense? Okay. So, right, so exactly, like, maybe the like trajectory matters, right? Like each of these updates, like ultimately we want group conditional mean consistency, but like each of these updates, as far as our analysis is concerned, like what's important about it is that it decreases squared error. Okay, and it always outputs a model that looks like this. And to Natalie's question, like, maybe we wanted to run for more rounds and have lower squared error, but like we didn't. But now that we know that it always outputs a model that looks like this, why don't we just minimize squared error over all models that look like this? Okay, that'll give us something that is only better in terms of squared error than anything that our iterative algorithm could have possibly given us. should be an easy thing to do. We're just minimizing squared error. It's convex subjective function over linear functions. These are just linear combinations of group indicators, so not a difficult optimization problem. And we should be able to argue that this will be like the only little thing we have to think about. But since ultimately squared error isn't really our objective, it's just a nice to have. Our objective is group conditional mean consistency. That if we go this direct optimization approach, we also get group conditional mean consistency. Perfect group conditional mean consistency now, not alpha approximate.
So are we optimizing subject to a bunch of constraints? Like, could we?
No.
So you're saying you have this expression and you're going to minimize?
Yeah, I'll write it down. But like the idea is, I've written things like this because lambdas are the parameters, right? So we want to optimize over lambdas, this thing. And we'd like to minimize the squared error of this thing. Okay, so we've got like G real numbers. We've got a model that is just a linear function of those G real numbers. And we would like to find the setting of those G real numbers that minimizes squared error. So it's really a linear regression problem.
So I understand how every model went up. But what I don't understand is how we can say that every model of this form satisfies the group thing that we want.
Oh, we'll need to prove that. But if you think about it, you can probably figure it out. We'll prove it. But in the meantime, you can think about it and figure it out.
Well, if lambdas are all 0, then it certainly doesn't.
But then maybe that wouldn't be the optimal solution to the optimization problem.
The optimal solution
Oh, yes, certainly it's not that every function of this form minimizes, it is group conditionally mean consistent. The claim is that the thing in this form that minimizes squared error amongst all functions of this form must be.
Yeah, that seems likely.
I think so too.
I'm sorry, I'm confused about the definition of lambda. Is it matrix or is it vector?
It's a vector. So there's for every group G, right? So lambda here is like a real vector that has like G dimensions. There's one entry for every group in our collection of groups. That entry, if we want to express the function output by the group shift algorithm, we just set for every coordinate corresponding to little g, that entry equal to the sum of the shifts applied to the group in that coordinate. But more generally, there's like other functions in this class parameterized by the vectors in this vector space. Good. Other questions? Yes.
Because when we got before, more satisfied with
yeah, like basically, right? Like it follows from the fact that the output of this group shift algorithm has this form, and each step of the group shift algorithm reduces squared error. So suppose, we'll prove this after we give the algorithm, but like suppose it was the case that the thing that optimized squared error, was a function that wasn't group conditionally mean consistent. Then we could plug that thing as the initial function into the group shift algorithm. We could run it. We could make it group conditionally mean consistent and improve the squared error, but it would still have this form, and that would contradict optimality. All good questions. Other questions? Okay. Okay, so let's call this I don't know, maybe simple group conditional. And it's just a linear regression problem. So let's just let lambda star be the solution. to the following optimization problem. Minimize overall lambda. The expected squared error. This model f hat of x parameterized by lambda. And remember, this is just shorthand for the model looking like this. Okay, that's it. And we get the optimal solution, lambda star, and we output the function parameterized by lambda star. Okay, and let me just stress, like, not only is this, like an easy problem in that it's like a, convex optimization problem over linear functions, this is like literally linear regression, right? Like, it's like the features of each example are the vector of g of x values. It's like, g of x is 1 or 0 for each group. And we just want to find a linear combination of the features that minimizes squared error. So this has like a, this is like the easiest problem you can imagine. It has a closed form solution. This is the first, statistical method you learned. This is like linear regression. The claim is that if we want to group conditional mean consistency, it suffices to solve a linear regression problem over the vector of group indicator functions for the groups that we want group conditional mean consistency to hold with respect to. Okay.
Have an issue then, like a linear regression with our f hat not being like guaranteed to being on the 0, 1 interval?
On the 0, 1.
Like on an interval 0 to 1, the output.
So it is true that this thing will output something that does not necessarily predict numbers between 0 and 1. That is true. By the way, the group shift algorithm, as we've stated it, also has that problem. Because these shifts are, well, they're always matching the expected label on average over the group. So the average value over the group is always between 0 and 1. But it might be that for some particular examples, we go outside of 0 and 1. Now, for the group shift algorithm, there's actually a very simple fix to that, which is just at every round after you've performed this shift, just truncate anything that's bigger than 1 to 1, and truncate anything that's like less than 0 to 0. And since the labels are between 0 and 1, that truncation also only improves squared error. And so like that only actually helps your analysis and speeds up convergence. So for the group shift algorithm, as we've stated it, it also might output functions that don't have the range 0 to 1, but there's an easy fix. For this one, I don't know if there's an easy fix. And maybe that's one reason to prefer the group shift algorithm if you need the range to be 0 or 1, because of course, if you truncate the output of this thing, it will also only decrease the squared error, but it'll also take you outside of the model class that looks like this. And so it's no longer obvious that you couldn't have done better with some other lambda. So, okay, so good question. Short answer, yes. One problem with the functions output by both of these methods is that although they have the properties we've asked for, we haven't explicitly asked for them to have the right range, and they might not. For the iterative algorithm, there's an easy fix. For this algorithm, I don't know. Good question, though. Like okay, homework problem. Is there a version of this algorithm, by which I mean, like a one-shot optimization that maybe truncates things at the end, that can also be said to satisfy group conditional mean consistency? let me prove that this outputs something satisfying group conditional mean consistency, and then give you guys a short break. Okay, so let F from X to 0, 1 be any model. Let's similarly let G be any subset of groups. The model parameterized by lambda star, output by this algorithm, simple group conditional. Satisfies perfect, i.e., alpha equals 0, 0 approximate. Group conditional mean consistency. And moreover, if FT is a model output by our previous algorithm, group shift, then the Breyer score of this thing is only smaller than the Breyer score of the thing output by group shift. So like we might worry that group shift was order sensitive or something, as Natalie pointed out, and maybe we want more rounds or for a larger decrease in Breyer score. What this is saying is that okay, there's two advantages to this over the group shift algorithm. One, okay, obviously it's like a one-shot optimization thing. It's just solve linear regression. But also there's no alpha parameter. It spits out the thing that is at least on the distribution you've given it. We'll have to talk about generalization theorems, but on the distribution you've given it, it is exactly group conditionally mean consistent. And also it outputs something that has lower Breyer score than anything that the group shift algorithm could output. It has lower Breyer score than anything in the class of models that the group shift algorithm is constrained to, which that part's sort of immediate, right? Because the group shift algorithm outputs models that look like this, and we are globally optimizing over the set of those models to have small Breyer score. Okay, does that make sense? All right, it's 3. Why don't I give you a 15-minute break, and then we'll come back and prove this and think about generalization. So I'll see you back here at 3:15. Okay. So we were about to prove this theorem. Just to remind everybody, we're we have this iterative group shift algorithm. It always outputs a function in this parametric class. The potential argument was that every shift reduces squared error. So why don't we just directly optimize for squared error over the functions in this parametric class? Doing so is very easy. It's just literally linear regression. And so what is the claim that is supposed to be true? It's that if we do that, if we solve this optimization problem, for now ignoring sample issues, so I'm imagining we're solving it directly over the distribution, then the model output by this will be perfectly group conditional mean consistent. So none of this like alpha approximation nonsense anymore. And also it will have lower squared error than anything you could have gotten from the group shift algorithm. Okay. Okay, so the fact that it has lower squared error than anything you could have gotten from the group shift algorithm, that's immediate. It's just from our observation that the thing output by the group shift algorithm has this functional form, and we are like explicitly minimizing squared error over that whole class. So of course, the global minimizer has lower squared error than anything else in that class. The only question is, why does the thing output have lower squared error than why is it perfectly group conditionally mean consistent? Okay. Well, suppose it were not. Okay, so like there's some group out there for which this function output fails to satisfy that conditional on membership in that group, the average prediction of this function is equal to the average value of the label. Okay, that's like what it means to not be group conditionally mean consistent. Okay, so you know, there exists some G in our class such that if I look at the difference between the average prediction of our model and the label conditional on membership in this group, might as well square it. This is strictly bigger than 0, right? Like satisfying group conditional mean consistency is exactly the statement that this quantity is 0 for all of the groups. And so like not satisfying it is that this quantity is positive for one of the groups, at least one of the groups. You know, let's let delta equal the thing inside the square. Let's let delta equal the expected value of our model minus the label, conditional on being in group G. Note that this thing, of course, is not 0. And let's let f prime be the model that results from applying exactly the same patch operation that we use in our group shift algorithm. Okay, so let's let f prime be the model that results from applying our patch operation to the model output by our optimization algorithm on this group G that we supposedly fail to satisfy a group conditional mean consistency with respect to using this non-zero shift delta. Okay. So what do we know about this patch operation? Well, it's going to like decrease the Breyer score of the model. It'll decrease the Breyer score by the size of the group times the squared shift value. But for our purposes here, the only thing we need to note is that those things are both like non-zero. We don't care how much we decrease it. Okay, so like on the one hand, the Breyer score of f prime is like strictly smaller than the Breyer score of f hat. That was like one of the first lemmas we proved today, that this sort of shift operation, when there's actually a violation of group conditional mean consistency on a group that has, non-zero measure, and the violation is non-zero, strictly decreases the Breyer score. Okay, so we strictly decrease the Breyer score. On the other hand, we can write f prime as a model in this same class, parameterized by a vector lambda prime, where lambda prime of g equals lambda star of g plus delta, and lambda prime of g prime equals lambda star of g prime for all of the other groups g prime not equal to g. Right, because what is the shift operation doing? It is just shifting points in group G and doing nothing to the others. So that's equivalent to just like shifting the parameter on lambda G on group G, right? The shift operation is just like, this was sort of our first observation. The shift operation just corresponds to shifting this parameter lambda G by delta. Right. But that's a contradiction, because we would have produced in this case another model in the same class that has lower squared error, but that contradicts the optimality of lambda star. Lambda star was the thing that minimized squared error in this model class. So this can't happen. And so the thing we supposed, that we didn't satisfy group conditional mean consistency, that can't happen either. Right? The output has to satisfy group conditional mean consistency. Make sense? And you can do the same thing for quantiles, where for quantiles, you would minimize pinball loss rather than squared error. Okay. So now I want to talk about doing this on data, finite sample guarantees. And you could analyze the group shift algorithm in a finite sample way. We'll analyze a similar algorithm later when we talk about multi-calibration. Let me analyze like this kind of algorithm. And like an important parameter, in fact, like, this algorithm, it's linear regression, right? So we're going to run into like exactly the same kinds of problems that we run into when we start thinking about analyzing linear regression, which are basically sort of like, you might worry about like numeric instability, right? Like if you've got like sort of collinear points, the condition number of your matrix is like super large, then like what can happen is, among other things, like the norm of your solution, the magnitude of your regression parameters just becomes like huge, and then you're kind of out of luck. And so we are going to do sort of the same kind of thing that you might do if you're worried about generalization for linear regression, which is add a regularization term. Right, so if you know about like ridge regression, that's just linear regression, where we add like a small penalty for the L2 norm of the parameter vector, or maybe you've heard of lasso. That's just linear regression, where you add a small penalty for the L1 norm of the regression parameters. That's what we're going to do too. But like one of the reasons that helps is it guarantees that the solution to this thing, like at the moment, it's like totally unconstrained. You might worry that these lambdas, are somehow like, even though we need that the average predictions over every group are, numbers between 0 and 1, you might worry that like it's taking advantage of like massive, cancellations, like for one group, that lambda G is like 1 million, for another group, it's like -1 million, and somehow things are in some, knife edge way, like, canceling out for the most part, but that would make generalization claims a mess. If we add like a regularization term, we guarantee that that can't happen. So that's what we're going to do. We're going to do, like, basically, we're going to replace linear regression here with lasso. We're gonna add an L1 regularization term. Right. So what's the L1 norm? Well, if I've got a d-dimensional vector, a d-dimensional real valued vector, the L1 norm of V, written like this, is just the sum over the d coordinates of the absolute value of each of the coordinates. Okay. And I'm just going to modify this algorithm so that rather than just minimizing squared error, what I'm doing is I'm minimizing squared error plus eta times the L1 norm of the parameter vector, where eta you should think of as some small number that I'll pick later to, optimize for the generalization bound. Okay, so is it clear what the algorithm is? I'm changing the objective a little bit. Now what I'm doing is, rather than just saying minimize squared error, I'm minimizing like the convex combination of squared error and but I'm also putting a little weight penalizing the L2 norm of my parameter vector. The idea being, I don't want, but like somehow the generalization is going to depend on counting how many parameter vectors this thing might output. And, there's more parameter vectors with high norm than there are with small norm. And so I want to make sure that this thing outputs something with bounded norm. And that's what the regularization term is accomplishing. Okay, makes sense. Okay. So let's just notice that it's true that this algorithm now outputs something that has small norm. So let's let F, once again, be any model. I'm going to assume that we don't know that the output of this thing has range 0, 1, but I'm going to assume that the model you give it as input has range 0, 1. Okay, be any model with range 0, 1. The range 0, 1 is important here. And again, we'll let G be any collection of groups. Let's let D be any distribution. In particular, since we're arguing about generalization, there's going to be two distributions that we care about. So there's the real distribution, and there's the empirical distribution on samples that we're going to actually run this thing on. And we want the following claim to be true for both of those distributions. Then, this algorithm, maybe we'll call it simple group conditional regularized now, or for short, SGCR. Outputs a model F hat parametrized by lambda star, such that the L1 norm of lambda star is not so big. In particular, it's at most 1 over eta, where eta is the weight that we put on the regularization term. Okay. Okay. Well, let's think about why that is. It's because squared error is bounded between 0 and 1. So suppose this wasn't true. Suppose the optimal solution to this problem had norm bigger than 1 over eta. Well, there's two components to this objective function. There's the regularization term, which is just eta times the norm. This term on its own would be bigger than 1 if we output something that had norm bigger than 1 over eta. Eta times 1 over eta is 1. The squared error, I don't know what it is, but it's definitely not negative. Like, squared error is non-negative. And so, you know, right, if this wasn't true, otherwise the objective value would be greater than 1, because it's, you know, just the regularization term on its own is greater than 1. And I claim that then that couldn't possibly be optimal, right? Because consider this alternative solution where I just choose lambda 0, which is like the all zeros vector. Well, what would the objective value of this thing be? Here, the objective value would be, well, you know, I'd get some model. You know, if the lambda vector was all zeros, it would just be my original model. It would have some squared error. It would be the Breyer score of my initial model plus 0, because the, you know, the L1 norm of the all zeros vector is 0. But the original model had entries bounded between 0 and 1. So the Breyer score of the original model is at most 1, which is smaller than this thing that was supposed to be the optimal solution to this optimization problem, which had objective value bigger than 1. Right, so that's a contradiction. Because yeah, but like the optimal, you know, there's always a solution that has objective value at most 1, so nothing that has objective value bigger than 1 could be optimal. Okay. Right, so the only thing we're not relying on any properties of this distribution. We're just relying on the fact that the, you know, Breyer score for a model whose entries are in the correct range can't be bigger than 1. Okay, so in particular, like, what's going to be useful about this is that it implies both that the optimal solution on the data distribution has norm less than 1 over eta, but also the optimal solution on the true underlying distribution, which we don't have direct access to, also has norm that's not too big. Okay, we're going to need to relate these two things. Okay, so what we want to do, but like we know that this thing is going to output a small norm solution. We want to count like how many small norm solutions there are, and you know the overall strategy is we're going to apply a Chernoff bound basically for every fixed model, and we're going to like count how many models could be output and union bound over all of them. Now, you might object that there's like continuously many models because these are real valued vectors. Even if I bound their norm, like there's still a lot of real numbers. So we need to like specify a little bit more carefully what we mean by counting. And what I mean is I want to count the size of the smallest finite epsilon net of the set of balls that of the set of vectors that have bounded norm. Okay. So some definitions. First of all, let me write B, C, D to denote the L1 ball in D dimensions of radius C. Okay, so this is just the set of all vectors, all D-dimensional real valued vectors that happen to have L1 norm at most C. Okay, so this is a ball with respect to the L1 norm that has radius C. Okay. Okay. And then I'll say n epsilon CD, which will be a finite subset, this ball. Is an epsilon net for the ball if for every vector x, all of the continuously many vectors x in the ball, there is some other vector x prime in the net, in the finite subset of the ball, such that the L1 distance between x and x prime is at most epsilon. Okay, so is it clear what an epsilon net is? I've got this ball of vectors, real valued vectors. So like there's really a lot of vectors crammed in there. It's like continuously many. But now I'm trying to take some finite subset of this thing, doesn't have nearly all of them, but what it's promising, what it's supposed to be promising is that it's got a point that's close to all of them, right? You point to any vector in the continuous ball, I can point to a vector in the net that is at distance at most epsilon from the vector you pointed to. Okay, so it's a covering. It's like an epsilon covering. Does it make sense? Okay. And so this is sort of what I mean by like counting the number of solutions. I can't count this. There's continuously many vectors in the ball, but this is, there might be finite epsilon nets, and I could try to count the size of the epsilon net. Okay, so the claim is that there is a finite epsilon net that has cardinality at most 1 plus 2 times the radius of the ball over epsilon raised to the d power. Okay, so the size of the net is like exponential in the dimension of the space, and has a more mild dependence on the radius of the space and on epsilon. Okay, is the claim clear? So his claim is that, the epsilon net is big, but like not that big. It's merely exponential in the dimension of the space. And like, remember how Chernoff bounds work. They sort of say, for some particular thing I'm trying to estimate, that is the average of something, like the squared error of a single model, then with probability 1 minus delta, my in-sample quantity is comparable to my out-of-sample quantity up to like a term that depends on log of 1 over delta. So if I want to like union bound over some set, maybe like an epsilon net, I have, that comes into my delta. I want to like fail to have estimated the quantity with probability, for each element of the set, only delta over the size of the set. So I can say with probability 1 minus delta, I get them all right, which means that the size of the set is going to come into the bound inside a logarithm. So being merely exponential in the dimension is pretty good. That means I'm going to pay in the end only linearly in the dimension. Okay. So, questions about definitions? Let's prove this. Let's let n epsilon be a maximal subset of epsilon separated points. Okay, what do I mean by that? I mean that, what does epsilon separated mean? I mean for any lambda and lambda prime in my set, there's got to be distance, L1 distance, at least epsilon between them. Okay, so pairwise, they're all epsilon far apart. And okay, so that's what epsilon separated means. Maximal means there's no, this is a subset of points from the ball. There's no point that there's no additional point from the ball that I can add to this set that maintains the epsilon separation property. Okay, so I've got some set of points. They're all epsilon far apart from one another, and there's no other point from the ball that I can add to the set that will maintain the epsilon separation property. Okay, does that make sense? Maximal set of epsilon separated points. Okay, so note that this thing must be an epsilon net. Okay, why? Well, if it wasn't an epsilon net, that would mean that there was some point that was epsilon far from every single thing in here. Right, like being an epsilon net means whatever point in the ball you show me, I can snatch out for you a point in my net that's epsilon close to it. So if it's not an epsilon net, that means you can point to something in the ball such that for every other point in the net, the distance is further than epsilon. But if there was such a point, you could add it to this and it would maintain the epsilon separation property. So if I have a maximal set of epsilon separated points, it's got to be an epsilon net. Does everyone buy that? Okay. So let's consider the union of balls, L1 balls, of radius epsilon over 2. Centered at points lambda in this net. Okay. So I'm going to draw, centered at each of these points, balls around them that have radius epsilon over 2. Okay. So these balls are disjoint, right? Because all of the points are epsilon separated. So, if it's epsilon, if me and Ira are epsilon apart and my arm is length epsilon over 2 and their arm is length epsilon over 2, they don't touch. Right, so I can do this and that sweeps the ball. Okay. So I can draw these balls on their disjoint, which means if I look at the volume of all of these balls, it is just the sum of the volume of each of these balls. I don't have to worry about like subtracting off the intersections because there are no intersections. Okay. So their total volume is just the size, the cardinality of this set times the volume of any one of them, right? Times the volume of a d-dimensional ball that has radius epsilon over 2. Okay, let's say this is the notation for the volume of a ball in d dimensions, an L1 ball in d dimensions that has radius epsilon over 2. Okay, so the volume of the union of all of these balls is just the volume of any one of them times the number of balls because they're pairwise disjoint. On the other hand, right, so like this is a ball of radius c. I might, the balls I've drawn around the constituent points, they might extend outside of this because maybe there's a point right on the boundary here that has, norm C, and then I draw like a ball around that extends outside. But the balls I've drawn around the points inside this set have radius epsilon over 2. So the union of all of these balls has to be inside the ball of radius like C plus epsilon over 2, right? Can't extend outside that. Okay, so they're right, like the balls are all a subset of the d-dimensional ball that has radius C plus epsilon over 2, which means that their total volume, the total volume of all of those balls, which is just a cardinality of the points in this set times the volume of a ball that has radius epsilon over 2, has to be less than the volume of a d-dimensional ball that has radius C plus epsilon over 2, because they're contained within it. And so the cardinality of this set cannot be more than the ratio of the volume of a d-dimensional ball of radius C plus epsilon over 2 over the volume of a d-dimensional ball of radius epsilon over 2. At which point you might like look up on Wikipedia what is the volume of like a L1 ball in d dimensions. But actually, like it doesn't, when you look up the answer, it's pretty intuitive. There's some form, if you actually want to know what the volume is, there's some formula that's maybe not so intuitive. But if you want to know what the ratio of the volume is, it's very easy. This is the same for all balls in d dimensions, right? Like if I have an object and I scale it up by a factor of 3, how much has the volume changed? Well, in 3 dimensions, like by 3 cubed, and in d dimensions by 3 to the d. Okay, that's true for balls of any norm. And so this is just actually the ratio of the radiuses raised to the dth power. Okay, this is just, well, the radius of the bigger ball is C plus epsilon over 2. The radius of the smaller ball is epsilon over 2 raised to the dth power. And this is just 2C over epsilon plus 1, which is what we wanted. Okay, so we've just constructed an epsilon net by thinking about balls. Okay. So, what good is an epsilon net? So what I want to, what's good about an epsilon net, one thing that's good about an epsilon net is it's finite. So I can union bound over all of the points in the net. right? So I can like apply a Chernoff bound and a union bound, and I can say, look, as long as the amount of data I have is, like bigger than D, because the, exponent here will come out as a linear term when I take a log, then, like my estimate of squared error, say, in sample for any model parameterized by something in the net is close to my estimate out of sample. But like, like most things are not in the net. What if I output something that's not in the net? Well, what I want to argue is that the squared error is Lipschitz, as a, that I can approximate the squared error of anything with the squared error of the function parameterized by the closest parameter vector in the net. But I'll lose something as a function of epsilon, but like if I wiggle the parameter vector only a little bit, I wiggle the squared error by only a little bit. So the general form of the argument is we're going to say, okay, what's the squared error of the thing output by this model out of sample? It's minimized the squared error in sample. First thing I'm going to do is I'm going to wiggle the parameter vector to the closest thing in the net. I'm going to say, since epsilon was small by construction, that didn't change the squared error too much. Then I'm going to say, okay, once I've got something in the net, now I can argue that in sample and out of sample, the errors are similar. There were only finitely many things in the net, and I union bounded over all of them. Okay. And now I want to compare it to the optimal thing out of sample, which again might not be in the net, but it's close to something in the net. So I'll wiggle it again. That's the basic outline of the argument. Okay. So we need to argue that squared error is appropriately Lipschitz. So let's let lambda and lambda prime be 2 points in the radius C ball of dimension equal to the number of groups that we've got. So 2 parameter vectors that might be output by this algorithm. And they're close, meaning lambda and lambda prime are within epsilon in L1 distance. Okay, so they're nearby. One of them might be a point in the ball, the other one might be the closest point in the net. Then, example by example, if I look at the squared error of a particular prediction on a particular label made by using the parameter vector lambda, and I compare that to the squared error of using the parameter vector lambda prime, this is at most 2 epsilon times the radius of the ball. Okay. Okay, so this is basically by direct calculation. I can write out the squared error, which I've already, not write it out. The squared error according to lambda minus the squared error according to lambda prime. And the y squared terms cancel. And so I just get, well, yeah. It's f of x lambda squared minus f of x lambda prime squared plus the cross terms plus 2y times x lambda prime minus f of x lambda. And this I can factor as the difference between f of x lambda and f of x lambda prime times the sum of f of x lambda plus f of x lambda prime minus 2y. Okay, now let's think of each of these terms. Remember, what is the form of f of x lambda? It is just, well, it's f of x plus the sum of the lambda g's times the group indicators, but the group indicators are numbers between 0 and 1. So, well, they're either 0 or 1, but in particular, they're between 0 and 1. So what is the difference between f of x lambda and f of x lambda prime? Well, you know, this term cancels out, the f of x term cancels out. What I get is just the sum of all of the group indicators of something that can be upper bounded by the absolute value difference between lambda g and lambda g prime. I mean, these differences might like cancel each other out, but in the worst case, they don't. So the absolute value difference between lambda g and lambda g prime times a number that could be 0 or 1. If it's 0, it only helps me. The worst case is that all of the g of x's are 1, and that all of the differences between lambda and lambda prime are working against me, in which case this difference is exactly the L1 distance between lambda and lambda prime. So this first term I can bound by the L1 distance between lambda and lambda prime. And this second term, well, again, how big can these things be? As we already observed, they're not guaranteed to, you know, the predictions, unfortunately, are not guaranteed to be between 0 and 1, but they can't be huge. Like in particular, they're bounded by the L1 norm of lambda. Okay, so this is at most the L1 norm of lambda plus the L1 norm of lambda prime. Okay, but by assumption, lambda and lambda prime are within epsilon. Oops, I wrote these numbers wrong. They're within epsilon in L1 norm. So this is bounded by epsilon. These things are within the ball of radius c. So this is bounded, each of these is bounded by c, and there's 2 of them. So this whole thing is bounded by 2 epsilon c, which was what we wanted. Yeah. Okay. So let's now apply. Okay, so what have we done so far? We've said, look, there's an epsilon net, it's not so big. For points that are not in the epsilon net, we can like relate them to the closest point in the epsilon net, and we don't lose too much in our estimation of the squared error. The next thing to do is to say, for anything in the epsilon net, the squared error is similar in and out of sample, like in our sample and on the underlying distribution. In fact, we don't want to say that just for a single point. We'd like to union bound over like a large but finite number of points. So let's do that. Okay. fix any finite subset of the ball of radius c and dimension equal to the number of groups. Maybe you should have in mind the epsilon net. Okay. And any delta greater than 0. And let's say that we've got a data set that consists of n points sampled IID from our underlying distribution. Then, with probability 1 minus delta over the randomness of the sample, for every parameter vector in our finite subset, when we look at the difference between the expected squared error of the model defined by that parameter vector as evaluated on the empirical distribution of our data set, and we compare that to the expected squared error of the same model, but now on the underlying distribution from which the data set was drawn, this difference is bounded by c plus 1 squared times log of 2 times the cardinality of this set that we're making a uniform claim over delta divided by 2n. Okay. Is the claim clear? And this is just because since we know lambda is in this ball of radius c, in particular, if I look at the value that the function might take on any point, well, it's trying to predict the number between 0 and 1. It would be great if the thing it predicted was 0 or 1. That's your homework question to think about whether there's a variant of this algorithm that can output a function whose range is 0 or 1. But I can't say it's bounded between 0 and 1 since I haven't done the homework, but at least it's bounded between negative c and c, because it's this linear function of the lambdas, and the lambdas just have bounded norm. So in particular, if I look at the thing that I want concentration over, which is the squared error, for any point x and y, the difference between my prediction, which is a number between c and minus c, and my label, this is at most c plus 1 squared. Right, the worst case is this is minus c and the label's 1, so I get minus c minus 1 squared, c plus 1 squared. Okay, so it'd be a lot better if this number was 1. We'd get a better concentration bound, but at least we can say it's not too huge. It's c plus 1 squared. Okay, so Hufting's inequality, which you have now all memorized, tells us that for any particular lambda, the probability that when I look at the expected squared error on the empirical distribution and compare that to the expected squared error on the true distribution, the probability that this exceeds t is at most c plus, is at most 2 times something that goes to 0 at a rate of -2 n t squared over c plus 1 to the 4th. And the final bound just comes from choosing the value of t that makes this right-hand quantity not just less than delta, but less than delta over s. So that we know that with probability 1 minus delta over s, this is true for each of the lambdas. And so with probability 1 minus delta, it's true for all of them simultaneously. Okay, so that's how the final bound comes out. And in particular, right, so what have we argued so far? We've said, okay, on the one hand, the squared error for anything in our epsilon net will be close in and out of sample. On the other hand, our loss function is Lipschitz. And so a corollary of those two facts is the following. If again, I've got a data set that consists of n points sampled IID from an underlying distribution, then with probability 1 minus delta over the draw of these samples, for every lambda in the ball, not just in the net now, for every lambda in the whole continuous ball, when we look at sort of error we get by estimating squared error in sample compared to out of sample. Okay, so when we look at the difference between the in and out of sample, squared error, this is at most, well, the term we got over there, c plus 1 squared times log of 2 over delta plus the number of groups times log of 1 plus 2c over epsilon over 2n. This is just the term we got over here when we plug in as our set S the bound that we proved on the size of an epsilon net for our ball. So we're going to union bound over our epsilon net now. Plus twice the bound that we got on the Lipschitz parameter of squared loss. Okay, and why is that? We just apply each of our lemmas in series, basically. You know, I'm interested in the generalization of, I'm interested in the squared error of lambda. Okay, what do? I snap it to the closest lambda prime in the net. In doing so, I pay 2 epsilon c. Then I apply the out of sample generalization bound for every point in the net. In doing so, I pay the out of sample generalization bound, where S here is the size of the net. But now, this is the out of sample error for lambda prime. I'm interested in the out of sample error for lambda, so I need to snap it back. And I potentially pay another 2 epsilon c there. And that's it. Right? It's just, this theorem lets us move between in-sample quantities and out-of-sample quantities for any point in the net. And then the Lipschitzness property and the fact that we have an epsilon net lets us move from any point out of the net to some point in the net, paying 2 epsilon c. So we just move into the net, out of sample, back out of the net. That's it. Okay, and of course we get to set C, right? So, choosing C optimally, just to minimize these two things, minimize the sum of these two things. Or to, yes, it's not minimizing it because then I would just set it to 0, but simplifying, choosing C to be equal to, oh no, sorry, choosing epsilon optimally. Right, because I get to pick what the epsilon net is. The smaller epsilon is, if I make epsilon go to 0, I can drive this term to 0, but I'll blow this term up and vice versa. So I get to choose epsilon. It's not even part of the algorithm. The epsilon net is just some fiction that I'm imagining to make this argument go through. Choosing epsilon to optimize these terms, we can make this less than or equal to basically twice the first term. 2c plus 1 squared times this thing. Okay, so let's put all of the pieces together. Fix any set of groups, any delta, and any model with range 0, 1. Let D be endpoint sampled from the unknown distribution. And imagine that we run this algorithm on the empirical distribution of samples. So the obvious thing, we run it on our data set. Okay. Then the model output, let's call it f of x with parameter vector lambda star. By our algorithm, simple group conditional regularized, run on the empirical distribution on our data set. Satisfies alpha approximate group conditional mean consistency. Not on our data set, but on the underlying distribution D, whenever two things hold. First, we need that the groups not be too small. Okay, so I'm going to require that the minimum probability mass on any of the groups be at least alpha. And two, n has to be sufficiently large as a function of alpha, or in other words, alpha has to be sufficiently small as a function of n. So alpha should be at most eta, our regularization parameter, plus 4 times 1 over eta plus 1 squared times square root of log 2 over delta plus the number of groups times log 1 plus 2 root n over n. And of course, we get to choose eta. Eta is not like a fundamental property of the problem. Eta is like a parameter of our algorithm. So, choosing eta optimally, this is less than something that's on the order of like log of 1 over delta plus the number of groups log n over n to the 1/6. Okay, so we'll prove this. It's, given what we've built up, basically given this theorem now, it's not so hard, but I just want to make sure we understand the statement of the thing we're proving. Okay, it's like we have this algorithm. It had a super simple analysis, assuming we could optimize on the distribution. And we can't optimize on the distribution, the real distribution. We don't know what the real distribution is. We can optimize on a data set sampled from the real distribution. And what this is saying is, if we do that with the appropriate choice of regularization parameter, then so long as none of our groups were too tiny, and so long as n was big enough, we satisfy not perfect, but approximate group conditional mean consistency out of sample, where we can make alpha go to 0 by just taking more samples. Okay, that's the form of the theorem. Questions about the statement? Okay. Now, let's see. Should I prove it or just tell you how the proof works? Very complicated. But there's a lot of lines of algebra. I'll just tell you how it works. So what do we have here? What we have here is a theorem that says, assuming the norm of the parameter vectors we're talking about isn't too big, then my estimate for the in-sample squared error of any parameter of that norm is close to my estimate for the out-of-sample squared error. Okay. Now, what does this regularization parameter do? It does two things. The first thing it does is it makes sure that the optimal solution to this problem has small norm, has norm 1 over eta. Importantly, it makes it tells us that the optimal solution, both in sample and out of sample, which are different things, they both have small norm, because we know it has small norm over every distribution. Okay. Now, how did the proof work when we optimized in sample? When we were directly optimizing in sample, how did the proof work for the statement that this thing satisfies group conditional mean consistency? It said, suppose the optimal solution did not satisfy group conditional mean consistency, then we could apply a patch operation. We could lower its squared error while staying within the same model class. That would be a contradiction. We sort of want to get the same contradiction, but like out of sample now. So we want to say, suppose in sample, we got something that was very far from satisfying group conditional mean consistency out of sample. We'd want to say that we could apply this patch operation, which would reduce the squared error out of sample by so much that it would have lower squared error than the optimal solution to this problem out of sample. And that would be a contradiction. Okay. Now, the fact that we've regularized means that we know that the optimal solution in sample and the optimal solution out of sample both have norm at most 1 over eta. So we know that since this is the optimal solution in sample to the squared error minimization problem, it is within twice this error term of the optimal squared error out of sample, because say lambda star is the optimal solution in sample, lambda prime is the optimal solution out of sample. You know, in the worst case, when I look at the squared error of lambda star out of sample, it's worse than I thought by this quantity. And when I look at the squared error of the optimal solution in sample, it's worse than I thought by this quantity. And so in the worst case, the thing that I thought was optimal in sample can be out of sample worse than the truly optimal thing by at most twice this quantity. Right? So I'm in business if I can argue that my group conditional mean, if my group conditional mean consistency error is so large that when I perform the patch operation out of sample, I improve my squared error by more than this, more than twice this quantity. It's no longer enough to like improve it by just some little amount. I have to improve it enough to get a contradiction, right? But the thing I found, I'm not sure is optimal out of sample anymore, but I know it's approximately optimal out of sample. So if there were a large error in group conditional mean consistency, then the patch operation would imply a large improvement in error. This is why we need to assume that the groups aren't too tiny. It would imply a large improvement in error, and that would contradict the approximate optimality of squared error. That's why we argued that squared error was close in and out of sample, even though ultimately the thing we care about is this group conditional mean consistency. Now, there's one other twist, which is that my patch operation, I know it's going to improve my squared error, but it might increase the norm of the lambda. right? The patch operation might increase the norm of the lambda by exactly delta. And so, lambda star, like, it's not the thing that minimizes squared error in sample. It's the thing that minimizes regularized squared error in sample. And similarly, the optimal solution out of sample minimizes regularized squared error, right? So like, the contradiction I need is that the patch operation improves the regularized squared error enough to get a contradiction, right? So it's going to improve, I understand how much it improves the squared error, but it might make the norm, the regularization term, worse. And so I also need to make sure that, I'm improving basically the squared error more than I'm making the regularization term worse. But I am.
You are okay, then that's the.
Yeah. Because I'm making the regularization term worse by at most eta times delta, the magnitude of my patch operation. And delta is eta, delta is the square root of alpha over the size of the group, if you remember, right? It's an alpha violation of group conditional mean consistency means the product of the size of the group times the square of the shift I would need to fix it is at least alpha. And so the magnitude of the shift I would need to fix it is the square root of alpha over the size of the group. And the size of the group we're assuming is at least alpha. And so this is only eta, at most eta. And so we just need to make sure that we improve the squared error by this plus eta. It's just a fixed number. And the details are in the notes. Cool. So I'll see you guys next time. I haven't forgotten about the project, so start thinking about projects. I'm going to start asking you to tell me what your projects are.
The Sivan paper you told me about, what